All right. And then with that, welcome to the FNL25 Challenge Parameters webinar. Whoops. Here we go. Your host today will be Mark Abotossaway for the the Mars Challenge. Brittany Nez will be discussing the Moon Challenge. And I will hand it over to Mark to start us off.
Yeah, good afternoon. So just an overview of today's presentation. We will talk a bit about the challenge definition or requirements, of course, from the handbook. I think many of you teams, or most of the teams, have kind of reviewed that in the first proposal report. Next, we'll talk about the sensors a little bit, and then we'll talk about the microcontrollers, of course. We'll follow it up with testing, integration, and then data and results. Next. So the order, I'm going to talk first about Mars over the first half of this presentation, and then Brittany will talk about the Moon Challenge over the second half. So for those who don't know me, I am Mark Abotossaway. I'm a Ojibwe Anishinaabe First Nation. I've been supporting FNL for 7 or 8 years now. I'm an alumni. I competed, led the University of Minnesota team back when I was an undergrad. And then I'm the engineering support for the Mars Challenge this year. And of course, I'm a structures engineer here at Blue Origin in Seattle. Next. All right, so challenge definition and requirements. For the Mars teams on the call, I believe all of you understand the Mars Challenge definition and requirements after reviewing all of your proposals. Of course, teams must research and select sensors to measure following parameters during the rocket flight. So of course, you'll have a set of sensors that measure and record data during the rocket flight in April in Kenosha. These sensors must be independent of the rocketry avionics. So you cannot use your COTS altimeter or your COTS GPS to collect the data. You cannot interface. They must be completely separate circuits, separate components. The sensors and microcontrollers do not need to be co-located. So we also give you the option to run multiple controllers with multiple sensors. You could have up to 5 controllers for your 5 sensors. And that allows you to kind of separate them in the rocket. Maybe one needs to go in the front, one in the back, and 3 in the middle, depending on what data you're collecting. And then sensors, just a reminder, sensors shall not inhibit the safe operation of the rocket components. So, you know, most for the Mars teams, especially, you all understand how a dual deploy works, and you need the motor ejection to occur for your drogue parachute. So do not try to plan to put a sensor or a controller in the way of, you know, that's going to prohibit the motor ejection event from occurring, or, you know, that's going to prohibit those parachute events from occurring. Next. So as we mentioned, teams must select an integrated suite of sensors in your rocket to measure and record various data. So again, from the handbook, we all know that the measurements or the data you're collecting are airspeed, pressure, orientation, acceleration, and deflection. So also note you may need additional hardware to be used with the sensors. For example, airspeed. You may need a pitot tube or something in the airstream, right, that collects the data first and brings it on board to your sensor. You know, so that, you know, you may need additional hardware for your orientation sensor, for example, or your accelerations, right? If you're looking at load cells or whatnot. So think of that hardware as well as part of the sensor. Even though the sensor itself is kind of like the electronic component, just be aware you do have additional hardware requirements. Considerations for your sensor selections should include cost, size, performance, reliability, sampling, etc. There are various other, you know, considerations making your component selections. I did highlight size. You know, given it's kind of a balance between your choice of rocket airframe and what size of sensors you choose. Of course, if you choose the smaller stuff, you could put it in more areas, but it just takes more time to integrate. And usually the smaller components do cost a little bit more. So that's a trade-off that you'll need to study and make your selections. Next. I just wanted to highlight some sensor examples without kind of giving away too much. Like I don't want to be here presenting and telling you which airspeed sensor to use or which IMU to choose. There's no preference. We're not here to give you guidance on which manufacturer is better than others. Of course, so this kind of slide just kind of showing a bunch of sensors that, and there's dozens and dozens of sensors out there. You can measure everything from light to, sonar to, there's a camera sensor there in the bottom. And then also I wanted to point out for the Mars division, 5 sensors is the minimum. If you have the time and the budget and you're feeling, ambitious, you guys can put in as many sensors as you want. If you want to have a camera running in or multiple cameras running to your microcontrollers as well. If you want to measure temperature and pressure or, other things as well. Please focus on, making sure that the 5 competition sensors are kind of integrated and working first. Before you go off and decide to start adding other sensors to your package during the flight. Next. Moving on to the microcontroller. So again, your team must select a microcontroller to be used to control your sensors and store the collected data. Teams can use any suitable microcontroller. There's tons of controllers out there. I mean, the 2 populars, right, Arduino and Raspberry Pi, but there's other controllers out there. Teams can select more than one microcontroller. Like we mentioned, you have 5 sensors for Mars. You can use up to 5 microcontrollers if that's what you prefer. Teams also can select different microcontrollers. So maybe for an experiment or for your choice of sensor, you decide that the Raspberry Pi works better in this measurement and the Arduino works better for a different measurement. So of course you can mix and match the microcontrollers. There's nothing saying that you have to have one brand or one style in the Mars division. And again, consideration should also include cost, performance, size, data storage. It's the same considerations we make for sensors. And again, size is the big ones because the microcontrollers are going to be bigger than the sensors themselves, right? So again, maybe you want to choose a micro or nano type microcontroller, something that's smaller and fits into a smaller cavity within the rocket. And you're kind of sacrificing capability at that point or functionality. Of course, the bigger microcontrollers will give you more, capability. But depending where you put that microcontroller or where it's needed, right? So again, those are trade studies we want you to make and present in your reports. Next. So of course, there's a number here of microcontroller examples. I think after reviewing the Mars proposals, a number of you have to have chosen at least one of these microcontrollers here. I'm not going to go too much detail. That you guys do your research, and the Mars teams have been very, very good during their proposals, submitting and selecting their controllers. But realize there's other options out there other than the standard Arduino and Raspberry Pi. One of the things that's not super discussed in much of our documentation is in the handbook or the templates, for example. What we want you to start considering now is power. So we do not constrain your power sources for your sensors and your microcontrollers. So we want you to make those sensor selections, make those microcontroller selections, and then figure out what power you need to go with that, right? So a lot of you, of course, you're going to use LiPo power. But you should consider, wait time on the launch pad and the duration of flight. So make sure that your power considerations are, do we have to turn on the sensor maybe in the pit area before we go to the launch pad, right? Do you have to do some testing and calibration prior to launch? How long is that power needed for, right? Like, we don't want you to run out of power by the time the flight's done. A lot of times too in rocketry, sometimes you load your rocket on the pad and it needs to sit for 20 minutes while the winds kind of calm down or something like that. So being able to kind of turn on and turn off your devices is beneficial. And we'll talk about that in the next slide. One thing to note too about power sources, they should be secured against high accelerations and impacts. So from the safety perspective, right, sometimes we don't always have a nominal flight. If a parachute doesn't come out and your rocket comes down a little bit higher velocity than we expect, we don't want that LiPo to end up being crushed or impacted, right, which could possibly ignite a fire, and that'll cause a further damage, and that's a safety issue at the launch site. Next. Another thing we don't mention too much about in the handbook or the templates are the switches, but we want you to also contemplate these early while making your component selections. So we do not constrain which switches you use on your sensor microcontroller. Of course, options are going to include, a manual switch to power everything on somewhere in the circuit, or your Bluetooth power, right? So depending which microcontroller you have or you've selected, you may be able to turn on your entire circuit remotely while standing back in the pit area. So we just want you to understand and test the required distance to power on. So again, this takes some rocketry experience. So the Mars teams, you should know how far away, you know how far from the launch pads you need to be for that rocket to launch, right? So make sure to test your Bluetooth if that's what you're running, or you're running a remote power. Make sure you can power it on from quite a distance away, or power it off, for example, right? And then even testing the transmissibility, right? So again, this kind of ties to your rocket component selections. Some of you are selecting, phenolic airframes, which are fine. Some of you select the fiberglass airframe, but maybe some of you are selecting the carbon fiber airframes, right? So the transmissibility of signals through a carbon fiber airframe are not well known, or not the greatest. So make sure your rocket selection is tied to your component control, and you're integrating those two choices. And then of course, I just recommend mechanical switch in the circuit may be helpful for troubleshooting and power management. So even when you're in the pit area, right, and you got multiple things connected to the microcontroller and you're turning it on with Bluetooth, maybe you want to switch to your sensors so you can kind of cycle and turn things off and troubleshoot that way as well. Next. Component testing. I hope we're not cut off on the bottom there. It's kind of running. Yeah. So project management, of course, is an expected component of your reports. So we suggest you extensively test your sensors and microcontroller packages. These could, of course, be ground tests or flight tests. Not necessarily have to be flight tests. Ideally, best case scenario, you run it with your actual competition rocket before you come to launch weekend. There's other options as well. You could just put your sensors and controllers into a smaller, like a level 1 rocket, and fly that and test that. And if you don't have access to a launch site, you could put your sensors on a drone, for example, and you could go and test, make sure your drones, your microcontroller is recording the position of that drone, or the acceleration velocity of that drone. So there's multiple tests you can do, even just on the ground, right? You can drive in a car and make sure your sensor package is working properly. And then for Mars, we suggest you test each component individually. So you're just going to do as minimal testing as possible on one component when it arrives, just the bench testing. And usually there's, good guidance online to tell you how to set up and test something on the bench. We want you to test under ideal and extreme conditions if possible. So don't just test on the bench in a perfect room with an environment. Maybe you want to think about what kind of heat environment is this going to be under? Is this going to be under, a large acceleration load? How well does it work under vacuum, for example, right? So you're thinking of these different environments that your sensor and microcontrollers may be, experiencing over their life, and trying to test them in those environments as well. We also suggest you test the complete sensor assembly. So not only you're testing one component at a time, you're going to put it all together, right, and do your programming and whatnot. And then you're going to test the entire assembly, right? Make sure the assembly is recording data onto the microcontroller and logging all that. You can get that all out of the microcontroller after the fact. And then, you could do integration tests, for example, right? It's, putting the sensor and the microcontroller into the rocket. It may produce different results when it's inside the rocket, right, as opposed to on the bench. So making sure that your sensor and microcontrollers perform just as well in the rocket as they do outside of the rocket. And understanding, if there's any difference or variability between these two. We don't want you to be surprised, you do a bench test at home and you come and do the competition flight and somehow the results don't matter, don't make sense. So maybe it has something to do with the rocket itself. And then we also suggest you test the range of your remote power. So that kind of just relates back to the previous slide, right? If you're powering your stuff on with Bluetooth, make sure you understand that range. Next. Challenge integration. So the competition handbook, we do not constrain your integration as well. So you're free to put the sensors and controllers anywhere you want in the rocket. So there's an image there, kind of just a side view of a typical dual deploy rocket, kind of highlighting some possible places you may want to put a sensor. Of course, the avionics bay there, the green circle in the middle. It's a good choice, but it doesn't have to go there, right? I mean, your avionics bays, those are where your COTS altimeters are going to live, and that's possibly where your COTS GPS is going to live. So maybe you don't have enough space. Maybe the COTS components, which are higher priority than your sensor components, take up all the space. So maybe you thought about that already. You want to kind of grow that avionics bay to put the rest of your sensors in there. That's fine as well. But they don't necessarily need to go in there. They can also go in the nose cone, which is kind of a large empty section. And then for the Mars guys, you have that deflection sensor that may need to go near the rear of the rocket as well, right? So that one is going to be a little bit trickier because, maybe your controller sits in the rear close to the sensor in the fin, or maybe your controller sits up front and you're running wires to the rear. So you need to think about the different ways that you're going to approach that problem. So you can run, I know during proposal as well, there's been questions. You can run wires externally. So if you need to run out the airframe and down the side, even rockets today, such as Blue Origin's New Shepard rocket, we run our system runs outside the tank. So that's fine, that's acceptable. But just a reminder again, sensor packages must not interfere with the operation of the rocket. So, if you're putting a microcontroller somewhere, make sure you're protecting it from the black powder charges, for example, right? And it's in its own bay. You can create a separate bay or something, avionics bay towards the rear. Also want to note that sensors should be removable, but are required to be flown in flight, whether functioning or not. So, a lot of the times we get to launch weekend and sometimes we're troubleshooting, electronics and something's just not working. For the stability of the flight, we want you to kind of just keep the components in the rocket, whether it's functioning or not, just to keep that rocket in its flight orientation that we've simulated all the way up to launch weekend. Next. And then challenge data and results. So of course, you'll need to store your sensor data for post-processing. And then you're going to compare your sensor data to COTS data in the post-flight analysis. So again, consider your data rate and velocity of the rocket. Consider the amount of data need to be stored. So these are choices you're going to make, kind of alongside your microcontroller and any other, hardware that you need with your microcontroller to store this data. And then what's going to happen after launch weekend in your post-launch assessment report, you're going to compare the accuracy of your measurements, your challenge sensor measurements, say airspeed, for example, versus the airspeed as measured by your COTS altimeter. So all four other data parameters are usually measured by a standard COTS altimeter, except for deflection. So for the deflection, we'll want you to compare your flight deflection results against the bench test deflection. So kind of during maybe FR or CDR, we're gonna get you to test your deflection sensors on the bench. Maybe put a unit load under a 2G load or something like that. And then see how much deflection you got, and then you'll compare your flight data to the bench test. Next. I think that's it for the rocket. So we also have minimal rocket vehicle requirements this year. So again, your minimum airframe diameter is 4 inches. You can go bigger. There's 5, there's 6. If you're buying COTS, so we give you some options there. There's some room. Airframes for Mars can be COTS or fabricated or combination. So kind of just depends on your team experience. If you're good with fabricating or not, if you just want to go with the COTS is fine as well. And then your motors are limited to the K400 and the K535. Next, the final one. Challenge requirements performance. So there are performance requirements for your rocket flight. And these include those listed there. I don't think I'm going to go through and read all that, but your expected altitude for Mars is the highest of the 3 divisions, 3,200 to 4,000 feet AGL. Of course, across the board every year, mind your stability margins. They need to be greater than 1. Your minimum rail exit velocity needs to be greater than 52 feet per second. Of course, your thrust to weight 5 to 1. And then your drogue and main parachute descent rates are also listed there. So make sure you choose and arrange your components in your rocket to satisfy requirements. Don't forget about these requirements. And then with that, I think we'll turn you over to Brittany.
Thanks, Mark. Hello, everyone. My name is Brittany Nez. I'm helping out with the Moon Challenge this year. Uh, I'm the net, currently working for GE Aerospace as a controls engineer. Um, I think I've met a majority of the Moon teams at this point. You can go ahead, Rob. So for the Moon slides, we've done copy and paste over of the Mars challenge with being able to adjust the specific requirements to Moon. So a lot of these might be the same. That's just for easeability of reading later on when you're coming through. You don't have to go through the Mars slide deck portion to be able to find your requirements. They'll all just be in the Moon section. So a lot of these might be very similar to what Mark already talked about. I'll just highlight what specifically is different about the Moon Challenge. So this slide should be the same. Sensors, well, you guys are doing a sensor-based requirement or sensor-based challenge this year that will measure and record data during flight. Your sensors must be independent of the rocketry avionics, and then you don't need your sensors and microcontrollers to be co-located. And you want your sensors to make sure that you're going to have a safe rocket launch and won't harm the rocket. Go ahead and go next. For sensors, we have four sensors that the Moon Challenge team can choose from. Of the four sensors, you only need to choose two. You can do more, like Mark said, there's two is the minimum, but if you start leaning more towards that 5 range, then we can talk about maybe jumping up to the Mars challenge. But the sensors should be very similar to Mars. The only one we don't have is the deflection sensor. So you'll be able to choose from airspeed, pressure, orientation, and acceleration. You might have additional hardware that you'll need to include. We had some examples for sensors listed out in our handbook. So these are just visuals of the example sensors that we had called out in the handbook. One note that I've been getting from teams is that the BMP-085 pressure sensor is no longer available, so you'll have to look into another alternative pressure sensor to be able to use. But just want to note that since a few teams have reached out to me about that. And same things, you should be considering the cost, performance, reliability, sampling of your sensor choices. Next. For the Moon Challenge, we are constricted to one microcontroller. Teams will be using an Arduino Uno as their microcontroller. This can be any form of Arduino Uno. You can do an R3, R4. In the handbook, it's providing an R3 example, but as long as it's an Arduino Uno, you guys can use that controller. Next. And then for power, again, we don't call this out in the handbook, but it is something that you guys should be thinking about whether or not you want to have your power sources be remote and you can run it from Bluetooth. You want to test ranges for duration of battery life as well as duration of or range of distance to be able to turn on your battery power. You can also do a uh, manual power. Oh, actually, that's probably more on the switch side. We'll wait till the next slide for that discussion. Make sure that your batteries are secure. Um, we don't want a LiPo battery falling out, or uh, they can be pretty dangerous if they're not secured. Next, I'm sorry, going into switches here, you can do Bluetooth power on or manual switch. Both are fine. They've got their pros and cons on each side. As mentioned previously, you'll want to test your duration and your distance ranges for Bluetooth. For manual, you'll want to make sure that you'll be able to turn on your switches and have enough battery life to be able to uh, be waiting for launch. So take that into consideration. You might be waiting a little bit. You might be on launch pad for a little bit. Um, you'll have to test out battery life if you're going to be doing a manual switch. Um, a lot of this is very similar to Mark's comments. Go ahead and go next. For the Moon Challenge, testing in your reports, a report in your PDR, CDR reports, the testing plan is optional, but I would very much recommend you test out all of your components for the challenge as well as for flight. So I would strongly suggest you running through the same tests that the Mars teams are going to be doing, just to make sure that everything's working for launch day. Yeah, as I mentioned, you don't have to put it in your reports, but you should be running these tests. Okay, next. For challenge integration, we don't have to worry about the deflection sensor, so I'll remove those two circles at the bottom. You could put them there, but you might want to consider stability while you're placing your avionics bay. Make sure you run it through RockSim. And then again, consider the material choices that you'll have for your rocket to make sure that your sensors will be able to run through the material of the rocket. We should be good for this one. Next, Rob. And then similarly to Mars, we will have a comparison between the data from your sensor data and the COTS data that you'll get from altimeter data. That'll be done in a post-flight analysis and submitted in your PLAR report. So you'll want to make sure that you're considering data rates and the amount of data that will need to be stored on your controller, how you're going to combine that with all of your sensors and everything. And I think that's it on my side. Oh, never mind. We've got rocket requirements. These are the same as the Mars Challenge. You have a minimum diameter airframe of 4 inches. You can go bigger. I know a lot of the Moon teams chose that 4-inch diameter, and Frank was, cautioning you, make sure that your components fit. You can go to a bigger diameter. That's the minimum diameter that's listed out. So just keep that in mind. Your airframes can be kit, parts, or combination. And then we'll be pulling from the same motors as the Mars teams. Next. And then for performance requirements, it'll be the same for Mars, except for the expected altitude. You have a slightly larger range. You'll be able to go from 3,000 feet to 4,000 feet. But all of the other performance requirements for the rocket are going to be the same as the Mars Challenge. So we'll be checking this as we go through PDR, CDR, You'll just make sure that you list them out and we'll compare them to the requirements that we have here. And I think that's it. Any questions for either Mars or Moon challenge?
I know Steven had one in the chat. He was asking about sensor data. The flight means launch to landing, not launch to apogee. Mark replied, yes, it's over the entire range from your launch until landing. In case anyone didn't see the chat. Like, this would be a good time in case you guys have questions about, like, if you're thinking about a certain sensor, you could always just sort of run it past them, see if they think it would be feasible to include.
Or if we understand too, if you want to keep your sensors private and not share them with your competition, reach out to Rob, or if you have questions about your challenge. This is a competition. You can also just ask in private as well.
And also, prior to doing this competition, I'm gonna be repeating this quite a bit about be diligent on making sure when it gets close to testing your components that you don't have any brownouts, corrupt software that you create, static interference on your microcontroller, and inadvertently reversing the power connection, or design a protected power diode circuit of some type if you need to. Please tag everything you have to have. Power consumption management should be paramount. Test, test, test. There's nothing worse than when you get up to the pad and I have a sensor that it's not going to work. Well, you've got one sensor that doesn't work, maybe two sensors. It's going to take some time. We'll give you time at the pad. If your batteries are getting low for some reason, always have full charge batteries. Well, we will give you the chance to turn on your power devices like 30 or 40 or 1 minute before liftoff, just to make sure everything is operating properly. Bluetooth, be considerate to your neighbor Rocketeer. Make sure you're not interfering with his Bluetooth controls too. Just a caution, word of caution, because I know the Bluetooth Raven Featherweight, they warn you about being too close to your neighbor too when they activate their altimeter. That's all I got.
No questions. Don't be shy. If not, I'm expecting perfect reports at PDR from the Mars teams.
Right on.
Hey,
Could even just be general. Doesn't need to be about challenge. If you had questions about your feedback or going into PDR, if you have questions about the next milestone, questions about performance parameters. For the Moon teams, or even all teams, the Mars teams, those performance parameters come from your RockSim. So hopefully you've been on the RockSim since the start. If you're new to RockSim, tune in to next week's webinar. We'll review those performance parameters, how to change those in the simulations and how to get them out of your simulations.
Hey, they all got it, Mark.
Yeah, I guess we were perfect at explaining it.
all right. Going once, going twice. All right.
Don't be shy to email us if you think of something later.
Yeah, please reach out. Any questions you have, office hours are available at there's a link on the FNL calendar website, or our landing page. There's a new link at the top if you want to schedule office hours with me. But otherwise, thank you all for joining us. Hope you all have a good evening.